Okay, so in order to do this problem, when we're looking at expected value, really what it is just multiplying the probability by what you're expected to win. And that's all that it really is. So if we're expected to win $100, the probability of that is 10%. So we do that. And then we multiply the $25 times the 20%, and et cetera, and we add all those together. Okay, and that's how you can determine the expected value. And really what that's saying is that if we were to play this game 100 times, that expected value is what we'd ultimately win in the end. But a lot of times we look at expected value for the first time just to get an idea if it's a good game or not, if it's worth it. $15 per toss, we don't know if that's really a good deal or not. So let's try it out. So what we would do, and I'll write it out for you guys the long way first, and then we'll do some mental math here, is we would take that $100 and we would multiply it by 10%. So we don't really multiply something by 10% written out like that. We always change it to the decimal. So 10% is 0.10. And then we would add that to our $25. And the percent or probability of winning $25 is 20% or 0.20. Okay, and then we would then add that to the probability of winning the $10, which we're saying is the 0.30, plus the probability of winning $1, which is 0.40. Okay? So if we simplify that, hopefully these are fairly easy numbers. We can do them in our head. So 100 times 0.1, so 10% of 100, we know that's $10. Granted, that's good. You've already got it figured out for me. Awesome. And then 20% of $25 is $5. And if you don't know, you guys are more than welcome to use a calculator and do 25 times 0.2. Totally fine. 30% of $10, again, that's just $3. And 40% of $1 is going to be 40 cents. Okay, so any questions so far? Feel free to type in your notepads if you have a question. Or if you need help, you can do the chat. Edwin, you know that I'm breaking up really bad, so you must be at home. Sometimes it's easier to watch the recordings later or to go into the lab to watch them. They come through a little bit better. So sorry about that. Okay, so if we add those up, 10 plus 5 is 15, plus 3 is 18, plus 40 cents. That's $18.40 is the expected value of playing this game. So, all right guys, here's what I want you to do. Up on your screen at the top, do you guys see the little man with the hand raised? I know, Pranit, you found that earlier. See up here, you guys, with the little hand? What I want you to do is you're going to agree or disagree. So, hit agree if you think it's a good deal to play this game if it costs you $15 to play the game. Hit disagree if you disagree. So Alicia has a disagree. Okay, everybody has to vote. Brandon has an agree. Oh, just do you see the little hand up at the top, Heaven? With the hand up, the little person? So you would hit the agree button if you agree that $15 is a good deal, and then you would disagree if you think it is not a good deal. So it costs $15 to play the game, and the expected value of winning is $18.40. Emma, what do you think? Oh, Heaven, you raised your hand.
That means agree.
Okay, that means agree. Okay, that's fine too. You can raise your hand.
Or does that mean disagree?
You can say it means agree. That's good. All right, so we're getting a couple disagrees and we're getting a couple of agrees. Katie, what do you think? You have to vote, Katie. Agree or disagree? Assuming you are still with us. Oh, wait, where are you? No, I just lost you. Katie's not voting. Oh, you're typing. I see, Katie. Sorry. Okay. I was looking in the chat. And Pranit, good. Very good observation. So actually, if you guys look at Pranit's student number 7, she says on average you gain $3.40 per throw. So think about this. It cost you $15 per toss, right? And the expected value of winning is $18.40. So are you getting more than what it costs? Yes, you are. You are. You're getting more than what it costs. So on average, Granite is exactly right. You get $3.40 more than what it really costs you to play. So the chances are you could play this game over and over again, and you're going to come out with an extra $3.40, which is good, right? You want money coming in, not money coming out. So in reality, it is a good deal, very good deal. Okay, any questions on this one? Nope. Okay. And remember, you guys, there is a lesson in your week 4, I believe. It's in week 4 on expected value. So if you want to look at it a little bit more, go ahead and go to week 4 after we're done. Okay, so what we're going to do today, our objectives. We are going to review for your mid-unit exam. We're just going to go over that information. Just know that in week 5, we don't really have a lot of new material, and it's very light because it's your mid-unit exam. So all you guys are going to do is you're going to take a pre-test this week. And a test is really the wrong word. It's more like a skill assessment. I just want to see what skills you guys have so I can make sure to work those in for the next unit because we're done with statistics. We're starting our algebra unit. And it's advanced algebra, so I just want to make sure that you guys all have the foundation. The other thing that you're going to do this week is just do a little bit of review. So I think there's maybe one kind of real basic review activity. Otherwise, it's just take the mid-unit exam. So it's a pretty light week for you guys, which is nice because it's only a 4-day week anyway because we were off yesterday. Okay, so if you haven't caught up, make sure that you catch up before you take the mid-unit exam. Make sure you do the review and make sure you've checked your answers. All right, guys. So all these problems come directly from the review. So if you haven't done the review and you want to take notes, feel free. But again, I've posted all the answers, so hopefully you guys will be okay once you see the answers too. So I know on this one, so Heaven, this is kind of like the one you were asking me about. And this is a normal distribution, right? That the values have fallen in a normal curve. It's called a normal bell curve. And so anytime you have a normal distribution, you can make some assumptions about standard deviation. So in this case, the mean, which is the average on the survey, was 155. And, you know, I can draw a little, maybe kind of line right here. That's our mean right about there, right? 100, well, it's over a little bit. I'm too far to the left. But anyway, our mean is right about in there at about 155-ish. So maybe you're about right there. The standard deviation is 10. Okay, so that means that if I go 10 up from 155, that's 165. If I go 10 down from 155, that's going to be 145. Okay. So that distance represents one standard deviation on either side of the mean. Okay, so plus and minus one standard deviation. Okay, so as soon as I read this, I'm marking this on my curve so that I have this in my head. So the standard deviation is 10. And this will help me answer these questions. Determine the weight range that falls within one standard deviation from the mean. Well, I just found it, right? The weight range goes from 145 to 165. That is within one standard deviation of the mean. Okay, 145 to 165. And just to review, that represents 68% of all the scores. So that means 68% of the scores, 68% of these players' weights, or whoever's weights they are, is going to fall between 145 and 165. Or this isn't the players like the other one. Okay, and then it says what percent of the men surveyed fall between 135 and 175. So again, let's just figure out where that is. Well, 135 is down here. That's 2 standard deviations. 175 is up here. That's also 2 standard deviations. Okay, so what you need to know, and what I would bring into the mid-unit test, are those percentages if you don't have them memorized. So we know that plus and minus 1 standard deviation, I'm going to write the standard deviation like that, is equal to 68% of all the data. Okay, but I also know, and I can look on my chart, plus and minus 2 standard deviations is actually equal to 95% of all the data. So if this range is exactly 2 standard deviations from the mean, 2 to the right, 2 to the left, then I know that the percent of men surveyed, there's going to be 95% of the men surveyed are going to fall within that range. Okay. And that can be a little tricky for you guys. Um, but, you know, if you think about it and you have your bell curve and you keep track of those percentages, it doesn't change. So it doesn't matter what the numbers are. If you can figure out one standard deviation above and one standard deviation below, that's 68% of your data. 2 is 95. So what questions do you guys have on that? Oh, Franny, you're asking about the empirical rule. Yeah, versus experimental. Or did you have a question about that? And the standard bell curve, you know, we don't look at, and this could go along the lines with your question too, Prana, we don't really look at standard deviation if we have outliers or we have skewed data because that impacts our standard deviation. And then I see what you're saying, the empirical rule with the 68, yes, exactly right. If we have a skewed distribution, then those percentages won't hold up anymore. So assuming that everything is normal and we do fall on a bell curve, then that's the only time that this applies. That one standard deviation will represent 68% of your data. 2% will represent approximately 95, 3%, 99, etc. So you're exactly right. And we're just, for these problems here, for our purposes, we'll just always assume the normal standard bell curve empirical rule for that. So very good question, very good question. Okay, so anybody else have any questions about that? Evan, does that make sense as far as what you were doing? Because you had that 7, which was your mean, right? And then you marked the standard deviations at 6 and 8 because the standard deviation was 1. In that case, that was 1. So technically, if you're following what Pranit's saying, because we're going to assume everything's normal, or pretty close to normal, then 68% of your data is all going to have a range of, what did we say, 6 to 8 kind of a thing. How do you, that's just part of the given. You know, they've done all these studies, and if things follow that normal bell curve, if things follow like that, you know, then they've counted up, you know, all the data, and they found that, hey, within one standard deviation of the mean, 68% of our data tends to always fall there. So those are just set percentages.
So it doesn't change?
Doesn't change. So it doesn't change based on the problem, assuming that we have the normal bell curve. That's what Prana was talking about, the empirical rule in that situation, which is what we'll assume for our tests and things like that, if I ask you guys. Okay. Okay, well then let's actually move on. So determine the margin of error. So we did do some margin of errors on a webinar before, but I just want to make sure you guys are good. So remember that to find the margin of error, and this is a very simple calculation, we are just saying 1 over the square root of the sample size, which is 4,000, and that gives us the margin of error. Okay, so I'll just do that as an M. So if we solve that, then we can find the margin of error. So if you take the square root of 4,000, and I did that so that I wouldn't have to think too hard, you get 20. Otherwise, you can put it in your calculator, which works as well. And actually, it looks like, Pranit, you are typing. Oh, yeah, it isn't 20, the square root of 400, it is. So, and I think I meant for this to be 400 because I didn't want to have to do it in my calculator. Did you do 4,000 in your calculator actually, Pranit, or no? You did? What did you get? You're typing, because it comes out to be a, oh yeah, that's your complete, that's good. You know what, you're fine. But what I'm going to do is I'm going to actually take off the 0 because I don't want to come up with some, you know, small decimals. So let's just say we're going to be looking at 400. How's that? Okay. So if we determine the margin of error for a sample size of 400, that makes the standard deviation come out better. Hang on, hang on. Good thing you're here. Okay, so square root of 400 is just 20. Okay, and then if you do 1 divided by 20, you guys can do, you know, long multiplication, or if you know it in your head, you might know what that is. If you need to use a calculator, you can use a calculator. We could have even done the square root of the other one in the calculator, but I didn't want to get a lot of decimals. So 0.05. Okay. And this just comes out nice and neat. So it's just better. Okay, so we've got 1 divided by 20, which is 0.05. But if we're looking at margin of error, we can change it to a percent. And we always say plus or minus 5%. Okay, so I just changed it to a percent. Okay, one thing, you guys, when you think about margin of error, I want you to understand this too. And again, we looked at this last time. If you did a poll and you said that, I'm just going to pick a number, say 20, again, I'm just going to pick an even number, 20% of the people are going to vote for somebody as president, okay? But if I have a margin of error plus or minus 5%, what that really means is I don't know that 20% of the people are actually going to vote for whoever is president. It's really going to be somewhere between 15 and 25% just because of that margin of error. Okay, so it's not exactly accurate to say that you know 20% of the people are going to vote for somebody as president. You have to factor in the margin of error, and that's usually published whenever they do surveys. You guys will see it at the very bottom. So always pay attention to that because you know, these aren't rule of law here. Okay, so let's look at B. And I know you were doing B, but you erased it. So if we look at B, what sample size would provide a margin of error of 5%? And this is where some of you guys struggled the last time. Well, it's really easy if you just say, okay, we know it's 0.05. I'm going to change it back. Oh, this is why it's the same number, right? So actually, it's kind of easy. So 0.05, which is 5%, is equal to 1 over a sample size of n, right? Square root of n. And you would solve backwards. Well, we already know from the upper one that our sample size has to be 400 to make this true. Okay, so that's actually kind of easy. But if we were going to solve this one, remember that we can cross multiply, and when you do that, you end up getting the square root of n is equal to 1 over 0.05. Okay. And then what I would do is just divide that out. And again, you can use a calculator and just say, okay, 1, and we already know, but we'll just do it, 0.05. And that gets us the 20 that we knew. So we have the square root of n is equal to 20. And this is just kind of good practice for you guys with your algebra, because next week we're going to be doing a lot of this. To get rid of a square root, if you guys know how to get rid of square roots, you square it, right? That's how you undo a square root. So our final answer, and we just proved it, is the 400. But we knew that from the top one. Except for that I originally had 4,000, which is not what we wanted. Okay, you guys, questions on margin of error, what they mean, anything like that? You guys feel good? Evan, you good? Okay. All right, well, that's really all there is to margin of error. For us, for our purposes. So what does the z-score mean? What does z-score mean? And Katie, you can type. Granite's typing away. Evan, did you get to z-score yet? You didn't? Okay. Number of standard deviations from the mean. Exactly right. Katie's a no. You don't know? Okay. And Katie, I don't think you're trying to remember where you left off, but I don't think you've gotten to that one yet either. So when you guys get there, there's your answer. It's the number of standard deviations from the mean, and that's what, if you look at Pranit's numbers, student number 7, she wrote that in there, and that's exactly right. It's the number of standard deviations from the mean. So you may be 1, you may be 2, you may be 2.2 standard deviations, but the z-score finds that for you exactly. And here's an example here in B. It says determine the z-score for the value 28 of a sample distribution whose mean is 46. So you've got all this data, right, and you've calculated the mean to be 46, and you pick one value, 28, and you want to see how far that is from the mean. You remember that's valuable for you guys because if something is within 1 standard deviation of the mean, then that's a pretty normal value. But if it's 5 standard deviations away from the mean, like when we did that webinar with the weather, that is an outlier. That is pretty far from the mean. That is not a normal value. Okay, and we can look at standard deviation as well to kind of help us. But in this case, we're going to look at our z-scores. So the calculation to find the z-score, remember, if you guys have already done that lesson, is you take that data value, which is 28, and you subtract the mean from that, and then you just divide by the standard deviation of 6. Good. Grants can do all the work for me. Perfect. Awesome job. Awesome job. Okay, and again, if you guys want to use your calculators, totally fine. But if you can do it in your head, that would be awesome. Okay, so you do get negative 18, and that's divided by 6, which is negative 3 standard deviations from the mean. Okay? All right, you guys, so what do you think? I mean, type in your notes. Is 28 a typical value for this distribution, or is that pretty far from normal? What do you think? Okay, so Pranav, you're exactly right. It's pretty far from the normal. Okay, you guys, Evan, you can type this, okay? You can think about it. It's good. So it's fairly far from the normal because we know that most of the data, 68% falls within one standard deviation, 95% really falls within two, and 99% of the data is within three. But it's somewhat out there. That's not where the majority lie initially. Okay, so that can kind of help us. All right, so I did want to review a little bit with probability because we don't touch on that a lot, just because you did that, in previous years. So we have some basic probabilities of independent and dependent events. Okay, so kind of you're close, unless you're still keep going. But on this one, the probability of flipping a coin and getting either a head or a tail, assuming that it doesn't fall on the edge, because if we add that in, that changes everything. But the probability of getting a head is 50%, right? Yep, you're right. Good job. So the probability of getting a head is 50%. The probability of getting a tail is 50%. We all know that, right? 1 out of 2. But the probability of getting either a head or a tail, well, that's going to happen no matter what, right? You're going to fall on either or. So one way to look at that is the probability, and we write it like this, of getting a head or a tail. And it's really easy to see with this one because we know it's 100%. Okay, but if we write that out and we say, okay, well, we have a 1/2, the probability of a head is 1/2, plus the probability of a tail is 1/2. So I'm just showing you mathematically how it works. If you add those together, you get 2 over 2, which is just 1. Convert that to a percent, and you get your 100%. So the probability of getting a head or a tail is going to be 100%. All right, let's move on to our final. Okay, and again, I'm not going through the whole entire review, so if you guys have questions, definitely let me know. So Emma, do you understand where the 1/2, why it's not exactly 1/2? Yeah, okay, good. All right, so this one is a little bit more complicated, but it's not horrible. This just has to do with dependent events. So what that means is that the probability of one event happening depends on the probability of the first event happening. So one thing depends on another. Okay. So let's look at the problem. You just won a raffle. The winner gets to pick a prize from a box but can't look. In the box there are 3 iPhones, 2 Androids, and 4 Blackberries. So what is that? 9 phones. 3, 4, 5, 6, 7, 8, 9. So we have 9 phones. So we're going to write that. We have 9 total phones. Okay, so we want to know the probability of choosing an iPhone. So what's that probability? You are very fast. This is awesome. You're exactly right, though. There's 3 out of 9 phones that are iPhones. We can reduce that to 1/3. And then a lot of times when people think of probability, they think of percent, right? So if we divide that out, we have 0.333 repeating, and we can just round that to approximately a 33% chance of choosing an iPhone. That's an independent probability, right? That's one thing. It doesn't depend on anything. We just made a pick. But now if we look at B, oh, very good. Very good, you guys. If you look at B, now assume you get 2 chances to pick a phone. And when you pick the first time, the phone stays out. So think about that. If you pick the first time, the phone stays out, that changes how many phones you have, right? So that changes your probability for the second one. So that's called a dependent event. So you get to choose two phones, and you want to find the probability that you will pick an Android and then an iPhone. So I'm going to say probability of Android and then an iPhone. Okay, well, we're going to take these separately. So the probability of choosing an Android is 2 out of 9, right? Can't dispute that. Okay. And anytime we are saying and, we multiply. So did you guys all multiply? Okay, look, looks like Prana, you did. Good job. Okay, so now we want to know the probability that your second time it's going to be an iPhone. Well, we didn't pick an iPhone on the first one. We picked an Android, right? So we still have, how many iPhones? 3 iPhones, but how many phones do we have in the bag? Good, Heaven, very good. Only 8. Only 8. Okay. So the probability of picking an Android and then an iPhone is going to be 6 over 72. You multiply those. 3 times 2 is 6. 9 times 8 is 72. We can reduce that to 1 over 12. And then we can change that to a percent. Did anyone change that to a percent yet? And if we don't know, we can pull out our handy dandy calculator and say 1 divided by 12, which is 0.0833333 forever. Okay, and then we can just round a little bit and say that it's 8.3%. Okay, you guys, so that's all the review that I have for you as far as what I know that people were struggling with a little bit or that we had a little bit less of a lesson. So what I want to do, first of all, do you guys have any questions about this probability? Hey, is that you? Oh, were you one? Oh, you were one. Okay, you guys feel pretty good about the probability? Okay, how about in general as far as your review, things going on? Katie, no, don't erase. Oh, do you want me to go back? Yes? Okay, I'll go back. And remember, Katie, I'm recording this too, so I'll post it today and you'll have it as well. But anybody else, any questions about anything? Oh, I see you did a little wait. Okay. I just want to make sure. So if you do and it comes to you later, send me a message. Let me know. I'll be in the lab here at Central on Thursday and I'll also be in the lab at Gateway. But just know that starting next week, we start Unit 2A because it'll span multiple quarters. And we'll be starting our advanced algebra, which, yay, I like that. So you guys will like it too, I'm sure. But we just need to finish up Unit 1. So take your test and hopefully everything goes well. And we'll see you all next week at the webinar. All right, adios, everybody.